didn't do a ton of examples in the other videos for Chapter 9. I thought, it was kind of easy, like when you are just given sort of a lecture on hydrogenation, and then they give you hydrogenation examples. It's a little bit easier. It's a little bit harder trying to put everything together. So I thought it might be helpful to have a video where we have lots of examples from the different types of reactions that we've seen in Chapter 9. All right, so I have a couple different types of example problems. The first couple are like this. So we want to predict the products when one pentyne reacts with, in this case, two equivalents of HBr. So first we need to know what one pentyne looks like. Oops. So there's 2 carbons, 3, 4, 5. And so now when it reacts with 2 equivalents of HBr, so this is going to be hydrohalogenation, and this proceeds by Markovnikov addition. And because we're using 2 equivalents, I'm going to go all the way to the alkane. I'm going to add 2 HBr's, and the bromines will add to the more substituted carbon. And so my product is going to be 5 carbons long, and then I have bromines adding to the more substituted carbon. Okay, so I have the same starting alkyne, but now I'm going to be doing hydroboration oxidation. And so I'm starting with this compound. And then, so the hydroboration oxidation is going to add an OH, but we're going to add the OH to the less substituted carbon. So it's going to be 5 carbons. It's going to become an alkene, and then I'll have the OH here. And this is an enol, right? Enol. But we usually can't isolate the enol, and it tautomerizes to, in this case, because I have the alcohol is on the end, it's going to tautomerize to the aldehyde. So that would be our final product. Okay, so in this case, I'm reacting it with a strong base, and so this is going to deprotonate my alkene, and that's going to make it a good nucleophile. So then when I react it with an alkyl halide, I'll have an alkylation reaction. And so essentially we're going to add a methyl group onto the end of the one pentyne. So same starting material. And so I'm going to deprotonate it and then add that methyl group onto there. And so my product will be this compound. Okay, so I have a new starting material in this case. I have 2-hexyne. So that's 1, 2, 3. So I need 3 more carbons. 1, 2, 3. And I have sodium metal dissolved in liquid ammonia. And so this is the dissolving metal reduction. And so I'm going to convert my alkyne into an alkene. Using these reagents, I'm going to get the trans alkene. If I'd used H2 and a poison catalyst, that would have given me the cis alkene. So to get the trans alkene, right, I've done 1, 2, 3, 4. I need 5 and 6. Okay, so in the previous examples, we were predicting the products. Now we want to know what reagents I need to achieve the following transformation. So in this case, I've added just 1 HCl to my alkyne, and I've done it via Markovnikov addition, the chlorine added to the more substituted carbon. And so if I'd used 2 equivalents of HCl, that would have given me an alkane with 2 chlorines, but we use just 1 equivalent to just get the alkene. Okay, so a similar reaction here, but now the bromine has been added to the less substituted carbon. So to achieve that, I'm going to use HBr. And to get the anti-Markovnikov addition, just like we did with alkenes, if I do this in the presence of a peroxide, that will give me the anti-Markovnikov addition of bromine. All right, in this case, I'm going from the alkyne to the alkene. So I've done this via reduction. If I just used hydrogen gas and a metal catalyst, that would have taken me all the way to the alkane. The way we would have stopped at the alkene, in this case, it's not cis or trans, so we could either use dissolving metal reduction, which we've seen before, or we could use hydrogen with a poison catalyst. So one of the poison catalysts we learned was Lindlar's catalyst. All right, in this case, I've converted my alkyne into a carboxylic acid, and I have a terminal alkyne here. And so the reaction we learned that produced carboxylic acids was the ozonolysis. And we learned that if we had a terminal alkyne, that gave us the carboxylic acid, and then the other product that they're not showing us is carbon dioxide. But to do ozonolysis on an alkyne, we'd use ozone and then water. All right, here's another case where I need to predict the products. Now, in this case, I'm using excess chlorine, right? So this is going to completely halogenate my alkyne, and so I'm going to end up with a tetrahalogenated alkane. To draw the product, I think the easiest thing to do is figure out how many carbons I'm going to have in my chain. So 1, 2, 3, 4, 5, 6, 7, 8. So I have an octane, 2, 3, 4, 5, 6, 7, 8. And on the second to the last carbon, I'll have a methyl group. And then the chlorines will be on carbons 1, 2, 3, and 4. Will each have 2 chlorines. So here's carbon 3. It'll get the 2 chlorines. Carbon 4, the 2 chlorines. All right, in this case, I'm doing a couple different reactions. So first, we're going to react it with excess NaNH2, right? And we learned about this reaction in the preparation of the alkynes. So if I have an alkyl dihalide and I react it with excess strong base, that's going to turn it into an alkyne. But we're going to end up getting a terminal alkyne, right? We're going to get our triple bond here. But because we're not then reacting it with water, we're not going to protonate that alkanide ion, which is going to leave it as a good nucleophile. And so then when I react it with the alkyl halide, I'm going to add an ethyl group onto the end of that alkyne. And then when I hit it with H2 and a platinum catalyst, that will reduce my triple bond and take me back to an alkane. Right, so when I react this with excess NaNH2 and I don't then react it with water, that's going to give me the terminal alkyne. Because I don't react it with water, I don't protonate it, and so this is going to be a good nucleophile. So now when I react this with the alkyl halide, I'll get an SN2 reaction, and that's going to end up giving me an ethyl group added on to the end of my alkyne. And then in the last step, when I react this with hydrogen gas and a platinum catalyst, that will completely reduce my alkyne here and convert it into an alkane. And so my final product, and I have 1, 2, 3, 4 carbons there now. So there's 1, 2, 3, 4. And so that would be my final product. Okay, we have another multi-step process. So the first thing we're going to do is react this with Br2. And so that's going to convert my alkene into this compound. Just like in the last case, when I react this with NaNH2, now I've got water, so that's going to turn me back into my neutral alkyne. So after steps 2 and 3, I would have that compound. And then with the last step, I have acid catalyzed hydration. And so that's going to give me a Markovnikov addition of an OH. But as we saw in the previous example, right, this enol is not going to be stable, and it's going to tautomerize to the ketone. And so this will be my final product. Okay, one last example. In this case, we're going to draw the mechanism for the hydroxide catalyzed tautomerization of this enol. And I said in the earlier videos when we talked about hydration, I want you to be able to draw. In this case, we're using hydroxide, so this is the base catalyzed tautomerization. You also want to be sure that you can do the acid catalyzed tautomerization. So in the base catalyzed tautomerization, so I have my enol, and we'll get a proton transfer step with the hydroxide. So it's going to steal the proton. Those electrons will go to the oxygen. Let's try that again. All right, and then we can convert this to a different resonance form. So we can bring our lone pairs down. Pi bond becomes a lone pair there. And then if I react that with the water, we'll get another proton transfer step. And that will complete the tautomerization.